Last week, we derived the operating lines for the two sections of the distillation column, those sections being the rectifying section where R here is the reflux ratio, given as the liquid flow rate in the rectifying section over the distillate flow rate. The operating line for the stripping section is where VB is the boil-up ratio, given as the bottoms flow rate over the vapor flow rate in the stripping section. We then took the intersection of these equations to give us the Q line, where Z in this equation is the composition of the feed, and Q is the ratio of liquid in the feed to the total feed flow rate. Now we've looked already at how to draw the Q line and the rectifying section operating line on our XY coordinate system with the 45-degree line and the equilibrium curve drawn in. All right, to get the rectifying section operating line, you find the distillate composition here. That's where the rectifying section operating line intersects the 45-degree line, and then you draw a line with the slope r over r plus 1. You then draw in the Q line at the point of the feed composition. That's the total feed composition, not the liquid feed composition. And you give it the slope Q over Q minus 1. All right, so now the question remains, how do you draw in the stripping section operating line? Well, first of all, let's take a look at the stripping section operating line and its intersection point with the 45-degree line. To find the intersection with the 45-degree line, we simply set x equal to y in this equation, and we get so the VB's cancel out, and we simply get that x is equal to xb. So just as the stripping section operating line intersects the 45-degree line at xd, and the Q line intersects the 45-degree line at the feed composition, the stripping section operating line intersects the 45-degree line at the bottoms composition, x sub b. Okay, so now the question remains how to determine the slope of the stripping section operating line. Rather than using the slope as given in the equation, what we're going to take advantage of is the fact that we constructed the Q line as the intersection between the stripping section and rectifying operating lines. Now that means simply that this point, where the rectifying section operating line and the Q line intersect, must be an intersection point with the stripping section operating line, because we know that all three lines must intersect because we constructed one line as the intersection of the other two lines. So we can draw in the stripping section operating line simply by drawing a straight line from xb on the 45-degree line to the point at which the rectifying section operating line and the Q line intersect. And now we have everything that we need for our McCabe-Thiele construction. We'll begin stepping down this just as we have stepped down for absorbers and strippers. Before we complete that, however, we need to consider some things about the feed stage location. Now, the way that we've come up with this construction is simply to say that at some point we must transfer over from the rectifying section operating line to the stripping section operating line. We haven't necessarily said at which stage we have to transfer over at. So we need to determine now which stage is the best stage to transfer from rectifying section operating line to stripping section operating line. Before we do that, however, let's take a quick look at the position of this Q line. All right, so Okay, so let's think again about the meaning of Q. Q is simply the liquid flow rate in the feed over the total feed flow rate. So when L is equal to F, we have a value of Q of 1. The slope of the Q line is then Q over Q minus 1. This means that when Q equals 1, we're going to have a line with an infinite slope, because we get a 0 in the bottom here. That corresponds to a vertical line. So if we have ZF right here, we draw a vertical Q line. And of course, the meaning of L equals LF is that the entire feed is a liquid. In this case, it's going to be a saturated liquid. We'll talk about subcooled liquids later. All right, so this line, vertical Q line, corresponds to Q equal 1, and it's a saturated liquid. If LF equals 0, in other words, if there's no liquid in the feed and we're feeding with a saturated vapor, then we're going to have a Q line slope of 0. So that's a horizontal line. So if we have a saturated vapor, we wind up with a horizontal Q line. And if we're somewhere in the middle, we get a slope between 0 and infinity, right, for values of Q going from 0 to 1. For instance, if 50% of our feed is liquid, then we'll have a Q value of 1/2. So we get 1/2 over negative 1/2, a slope of -1. And of course, that's going to be the line that is perpendicular to the 45-degree line, negative 45 degrees. And we fill in the rest of this as we go from vapor to liquid through here. Now, if we get a subcooled liquid, we'll wind up having Q lines with positive slopes. If we get a superheated vapor, we wind up getting Q lines with slopes less than 0. So let's start thinking about how we get the actual Q values for these situations. Now remember, what happens with a subcooled liquid in the feed is the liquid hits the streams running up and down in the column. So here we've got a feed that's a subcooled liquid. And when it hits the vapor stream coming up, energy from that vapor stream is going to be transferred into the feed stream, and the vapor stream will thereby condense and will add liquid going down into the stripping section. We have that in addition to the liquid that is coming down from the rectifying section. What this means in practical terms is that you're actually adding more liquid than you would if the feed were completely liquid to the stripping section. So this represents a value of Q that is greater than 1. Similarly, if we had a superheated vapor entering at the feed, it will convert some of the liquid falling down from the rectifying section into vapor. And that will add to the vapor that's rising from the stripping section. So here's a case where we've got a value of F that's, here's the case where none of the F is liquid, and in fact, it's turning some of the liquid into vapor. So it's actually reducing the amount of liquid at the feed. So we can think of this as a Q value less than 0. To calculate Q in either of these cases, we need to think of the amount of heat that's being transferred into the feed as a ratio of the enthalpy of vaporization of the feed, because that's going to tell us the amount of heat over the enthalpy of vaporization is the fraction of the feed that winds up converting into either vapor or liquid, right? So what we're going to figure out, the Q value is equal to the heat transferred into the feed over the enthalpy of vaporization at the feed stage location. For a subcooled liquid, Q then is going to be equal to the amount of energy required to turn this liquid into vapor, plus the amount of energy that we will need to bring the entering feed to its bubble point, because everything's going to reach equilibrium. So this is going to be the heat capacity of the liquid times the difference between the bubble point and the feed point, the feed temperature. Sorry, this is the bubble point temperature. This is the actual temperature of the feed. So that's the amount of energy we need to bring the liquid from a subcooled liquid to a saturated liquid. And this is going to be over the heat of vaporization. For a superheated vapor, the amount of heat transferred into the feed will simply be the heat capacity of the vapor times the difference between the dew point and the feed temperature, all over the heat of vaporization. This expression will yield a Q value less than 1. This expression will yield a Q value greater than 1. I'm sorry, quick error here. This isn't less than 1. This should be less than 0. This is going to be a negative Q value. Now let's consider where to transition from one section of the column to another. At the top of the column, we start in the rectifying section with tray 1 at the top of the rectifying section. We then step down, and we continue stepping down, and so long as we step between the equilibrium curve and the rectifying section operating line, we are in the rectifying section. The feed occurs at the point at which we step from the rectifying section to the equilibrium curve and then back to the stripping section operating line. In other words, the feed occurs at the junction between the two sections, as you might expect when we transition from one section to another. That's the definition of the feed. Now, if you look at this construction, you see that at stage 1, 2, 3, 4, 5, we're in the rectifying section. 6 and 7 are in the stripping section, and as a reminder, the final stage, stage 7, is the equilibrium stage at the bottom of the column, which is the reboiler. We treat the reboiler as an equilibrium stage. The 7th stage at the bottom of the column, or the lowest stage at the bottom of the column, will always be the reboiler. So this plot represents a distillation column that has 6 theoretical stages on the column and then 1 additional equilibrium stage in the reboiler. Similarly, we can switch to the stripping section before we get to the Q line. So here we have stages 1 and 2 on the rectifying section operating line, but then after stage 2, we switch to the stripping section operating line. So in this case, the feed stage is stage 2 because that's the stage in which we leave the rectifying section operating line, hit the equilibrium curve, and then return to the stripping section operating line. So we feed on stage 2 here, and it's exactly the same system, right? So here we're feeding at stage 5. Here we're feeding at stage 2. You see that when we feed at stage 2, we wind up with 1, 2, 3, 4, 5, 6 equilibrium stages. Again, stage 6 is going to be the reboiler, so this column has the reboiler and 5 equilibrium stages. Now look what happens, however, when we transition between the operating lines directly at the Q line. So where the Q line intersects the two operating lines is the point at which we decide to make the transition. Going over the Q line, we start at the rectifying section operating line, jump to the equilibrium curve, and then since we've crossed the Q line, we go back to the stripping section operating line. And in this case, we have 1, 2, 3, 4, 5 theoretical stages on the column. Again, stage 5 is the partial reboiler and equilibrium stage, and there are 4 equilibrium stages on the column. So what these diagrams are showing is that you get the minimum number of stages necessary to complete the separation when you transition between the operating lines with a feed stage as you cross the Q line. All right, so for this case, when we transitioned above the Q line, we required 6 equilibrium stages. Below the Q line, we required 7. And here, crossing the Q line, we only require 5 equilibrium stages. And of course, fewer stages are better because it means you can accomplish the same separation with a smaller column. Let's talk now about some of the limiting conditions of the distillation. So you'll recall, as with absorption and stripping, we're trying to look at the interplay between the number of stages required and the flow rate in the column. The flow rate in this case is given by the reflux ratio. The higher we set the reflux ratio, the more vapor and liquid will be flowing through the column. Right? So our trade-off can be written as follows. As the number of stages approaches an infinite number of stages, we're going to get a theoretical minimum reflux ratio. Similarly, as the reflux ratio approaches infinity, we're going to get a minimum number of stages. Let's think about this second case first, the theoretical case of minimum number of stages and an infinite reflux ratio. So the reflux ratio, again, is the liquid flow rate in the rectifying section over the distillate flow rate. If we set the distillate flow rate equal to 0, then we have the case of the reflux ratio approaching infinity. Notice that this is actually a realistic case. We can achieve a reflux ratio of infinity simply by closing off the distillate to the column. This is the case known as total reflux. And what this case really represents is feeding nothing into the column, taking nothing out of the column at either the top or the bottom, and simply allowing the vapor and liquid within the column to recirculate. It's boiled up by the reboiler, condensed by the condenser, and it just gets dumped back into the column at either side. So we've got a 0 feed rate, 0 distillate flow rate, 0 bottoms flow rate. We just have a column that's full of liquid and vapor, and it is just constantly recirculating, trapped in the column. Okay, so if we have a reflux ratio of infinity, we know that the slope of the slope of the rectifying section operating line is r over r plus 1. And of course, as r approaches infinity, the limit of this expression is going to be 1. Okay, so what this is telling us is that at total reflux, the slope of our rectifying section operating line is 1. And of course, we know that a line with a slope of 1 is a 45-degree line. So if we now draw our equilibrium curve and 45-degree line construction, we get something like this. And we set the distillate composition, where we're going to have our rectifying section operating line intersecting the 45-degree line. We set our bottoms composition, where we have the 45-degree line intersecting with the stripping section operating line, and we have our feed composition, where the Q line intersects. Now what this is telling us, right, the slope of the rectifying section operating line is 1, which means the rectifying section operating line is on the 45 degrees, and because one intersect with the rectifying section operating line is at xd on the 45-degree line, we know that the entire rectifying section operating line is identical to the 45-degree line. It doesn't matter now what the Q line looks like. In fact, when you think about it, there is no Q line because there is no feed. At total reflux, we're simply circulating what's in the column. But we know that the stripping section operating line does need to intersect the rectifying section operating line. The only way it can do that is if it's also lying along the 45-degree line. All right, so the construction for the minimum number of equilibrium stages, which corresponds to total reflux, a reflux ratio of infinity, simply goes between the equilibrium curve and the 45-degree line. We can count off steps. 1, 2, 3, 4, and we label them. 1, 2, 3, 4. We have 3 equilibrium stages on the column, and then the 4th equilibrium stage is the reboiler. So in this case, we say that the number of equilibrium stages at minimum, so n min is equal to 4. Now, let's look at the other side of the trade-off. Achieving the minimum reflux ratio at an infinite number of stages. Well, first of all, we'll think about what the McCabe-Thiele construction needs to look like at minimum reflux ratio. So we'll draw those axes again with the operating line and the equilibrium curve. And we're going to have XD up here, XB down here, and feed composition somewhere in the middle. We're going to have a Q line with some slope given by the composition of the feed. Here I've drawn a slope of about -1, so that indicates a feed that's equimolar in liquid and vapor. And we can then draw the rectifying section operating line based on the reflux ratio. But in this case, we're trying to determine the minimum reflux ratio. We don't know it a priori. So let's think about what that looks like. What's the minimum possible reflux ratio? Well, remember, the slope of the rectifying section operating line is given as R over R plus 1. Right? So we want to minimize this to minimize R, right? Because the limit as R goes to 0 is going to be R, right? So to minimize R, then, we need to minimize the slope. So we have the lowest slope possible. So think about all possible rectifying section operating lines. Slope gradually decreasing. Slope decreases in that direction. The most shallow slope that we can get is the rectifying section operating line running from XD to the point at which we have an intersection between the Q line and the equilibrium curve. If it's any more shallow than that, we don't intersect the Q line, the material balance for the feed stage under equilibrium, and we can never intersect the stripping section operating line, and we won't have a separation. We'll now draw the stripping section operating line. We know that it intersects with the rectifying section operating line and the Q line up here, so we can draw that. It's going to hit the 45-degree line at XB. Okay, so now let's think of what happens as we do our stair-stepping down from XD to the equilibrium curve. All right, so oops, step across the equilibrium curve, step down, step across, step down, step. And now you'll see we've hit a pinch point. And you'll recall from our discussion of absorbers and strippers that at this pinch point, you can just keep going back and forth between the two curves infinitely, getting into smaller and smaller corners between where the equilibrium curve and operating line come into contact. So you essentially have the case of an infinite number of stages. Right? So this is showing us that the construction for an infinite number of stages, which corresponds to a minimum value of R, occurs when the slope of the rectifying section operating line is such that the rectifying section operating line intersects with the Q line at the same point that the Q line touches the equilibrium curve. All right, so the slope of this rectifying section operating line is going to be R min over R min plus 1. And from this, you can get your minimum reflux ratio. Okay, so now let's put it all together. We're going to start out with the equilibrium curve in our liquid composition, vapor composition coordinate system. And we're always going to have the 45-degree line to go along with it. So our equilibrium curve will look something like this. Equilibrium data is going to be given in this problem. We're also going to know the required composition of the distillate, the required composition of the bottoms, and the composition of the feed entering the system. Now, what will usually be specified is the reflux ratio as some multiple of the minimum reflux ratio, so some value F times the minimum reflux ratio. For instance, you might be given, for example, R is equal to 1.3 times R min. And the question then will be, given this feed composition, this distillate composition, this bottoms composition, for this reflux ratio, how many stages do you need? You'll also be given one more thing. You'll be given the conditions of the feed. That is, how much vapor and how much liquid there are in the feed. That will determine your Q value. Okay, so the first thing that we have to do is draw on that Q line. So let's say that our feed is going to be a saturated liquid, which means that Q, which is equal to LF over F, is 1 because it's all liquid. This implies that the slope of the Q line, which is Q over Q minus 1, is going to be infinite. In other words, the Q line is going to be a vertical line. So we start at ZF and we draw a vertical line from ZF. We can now draw our minimum reflux ratio operating line. We're going to draw that from the intersection of the equilibrium curve and the Q line to XD. We now measure the slope of this line, and the slope of this line is going to be R min over R min plus 1. All right, so we'll now solve this equation for R min, and we will plug that R min into here to get our actual reflux ratio. Right, we then get the slope of the operating line for the rectifying section. So the slope for the rectifying section operating line is going to be R over R plus 1, using this R that we obtained by multiplying our R min from this construction times whatever multiple of R min that we are supposed to be operating on. So we now draw in a rectifying section operating line with the slope that we found. So let's say that's the slope that we get for that operating section rectifying line. Now we can draw on the stripping section operating line from XB to the intersection between the Q line and the rectifying section operating line. So that'll look something like this. Now we start at the top of the column and step down to the bottom of the column. Stage 1. Stage 2, we cross the Q line, which means that stage 2 is the feed stage. And now we start stepping back and forth between the stripping section operating line and the rectifying section operating line. Sorry, and the equilibrium curve. Okay, so we've drawn here our 1, 2, 3, 4 stages. Stage 2 is our feed stage. And stage 4 is our reboiler. In reality, we've gone further than we need to. We've gone maybe gone 3/4 of a stage towards equilibrium when we've reached X sub B. So in reality, this is going to be 1 reboiler, 1 partial reboiler, and 3 3/4 stages, 2 3/4 stages on the column.